Everybody, welcome to my Physics 2211 Lab Report for Oscillations. This is our table of contents. First, we're going to be going over purpose and instruction. Then we'll be going into physics principles and a preview of findings. Then we'll be talking about experimental details and tracker. That's also where I'll give you my initial conditions. Then we'll go into code details and glow script. Then I'll be talking about results and possible errors, as well as comparing and contrasting computational and experimental models. Then I'll be going into questions raised. The purpose of this lab is to fulfill the following: analyze the spring mass system and its associated energies, and to create a model that predicts the motion of the aforementioned system. These, when completed, will demonstrate the following physics principles: Newton's second law, energy principle, and spring force. So, looking at the first of those, Newton's second law is always relevant when we have any objects in motion because Newton's second law dictates the activity of objects in motion. But we're primarily going to be dealing with the energy principle and spring force in this lab. So, for spring force goes in the direction of L naught. So it's based on if a spring is stretched or compressed. If it's compressed, then it's going to be going in the direction of L naught. So it'll be a negative value, so it'll be going against wherever it's rooted. And then if it's stretched, then it'll be going towards wherever it's rooted because it'll be a positive value as L is greater than L naught. And spring force is non-constant as it changes with how stretched or compressed the spring is. And then the energy principle is that the change in energy is equal to change in kinetic energy plus the change in whatever relevant energies are in the system. So in this system, we're going to be having potential energy of spring and potential energy of gravitation, which are delta US and delta UG respectively. So the energy principle dictates the interactions of bodies when forces are applied within a system. They can be potential or kinetic, as I discussed. And in our case, there's no external work done because we have a closed system, an isolated system. So we shouldn't see any delta E. Delta E should be equal to 0. And formulas for US and for U grav are at the bottom. Keep in mind, these are not delta U grav and delta US. These are how to find potential energy, not change in potential energy. So change in potential energy would have delta X squared, and change in gravitational energy would have delta R instead of the values that you see there right now. For system and surroundings, our system is the object that is on the spring, the Earth, which is factored into the system by gravity, and then the spring itself. The surroundings are everything else, but nothing that affects the system, hence we have an isolated or closed system. So preview findings are that the computation model will very closely mirror the movement of the spring in the suggested video, indicating that the conservation of energy is accurately depicted by the real-world system. When I say suggested video, that's the one that Dr. Alicia Munoz gave us access to complete this lab. It was option 1 for the lab. So, going to experimental model, I used tracker to track the object in the spring video, and as you can see on the right, those were my tracker values. This is nothing out of the ordinary. We've seen this in the other 3 labs, so I think I can go ahead and move on. I think you get the idea of how this experiment was conducted. So, via that video, I got my initial conditions. So, you can see position and velocity are given there. Those are the initial conditions. So, the initial velocity was factored in as 0. We're assuming no force is applied on the object prior to it being released by the man in the video, and the starting position is as given, based on the axes that you can see here in pink in the model. And then B is a constant, and then the spring constant and relaxed length of spring were calculated using the spring force formula that I presented in the introduction. So, this is my computational model. So, as you can see, relevant values, or the most relevant values rather, are ball velocity and ball position, which ball velocity is using the velocity update formula that is dictated by Newton's second law, and then ball position is the position update formula based on the velocity update formula. So it's once again derived from Newton's second law. You can also see that the formula for E is located in the bottom left. E equals K plus UG plus US. That's exactly what I showed you guys at the beginning, except I had deltas next to them. So that the formula you can see on the screen right now is just the general formula for energy, but then the change in energy is when energy has a delta next to it, as well as all the other values having deltas. And then on the right side, you can see how we calculate potential energy of gravitation and potential energy of springs. And so you can see the ball's mass multiplied by gravity multiplied by ball's position y is how we're updating the gravitation potential energy. And then for spring, we're multiplying 1/2 times the spring stiffness and multiplying that by s squared, which is the length of the spring. And then ultimately UCE is the same formula there. This is the graph I ultimately generated using our models. So you can see this is the delta E graph, right? This is what I talked about in the intro. And as you can see, delta E equals 0. Which is exactly what you would predict in an isolated closed system. So that's great. That's very positive for our results. Exactly what we would expect. And you also see oscillations with the change in potential energy as it relates to gravity and change in potential energy as it relates to the spring. That makes sense intuitively, right? Because your potential energy for gravity is going to increase whenever an object goes up, right? Whenever it's moving in a positive y direction, because then gravity has more potential to act on it, right? Because it's actively resisting gravity. So that's where you can see delta U growing. And then delta U spring grows when the object moves in the negative y direction, because it is more stretched, right? And if the object is stretched beyond its L naught, then it's going to move towards L naught to correct that, right? That's how springs work. And so ultimately, the further stretched a spring becomes, the more potential energy you have. And so because those are operating in opposite directions, you see them oscillating opposite, which is exactly what we'd expect. So that's great. And then I have some sources of error up here. So some possible sources of error are tracking errors. I could have clicked the wrong place in the video. Another possible error is that the base of the spring may not be fully fixed or rigid, and so whenever the object is moving, then it could be jerking the body it's attached to via the spring around, which would then kind of add some confounding forces to the mix. Or the man who released the object could have applied force. It didn't look like he did in the video, but you never really know. He might have put a little spin on it or something, right? So those are possible sources of error. Although it doesn't seem like there's a lot of error. We predicted to be an isolated system, and there wouldn't be a change in energy, and then ultimately there didn't appear to be. So that's great. And then these are the experimental versus computational models. So as you can see, the experimental model doesn't model doesn't reflect the computational exactly. However, they have very similar trends. You can see their minimums and maximums occur at about the same time on every interval. However, they kind of vary a little bit in their x and y position, right? So that is a little notable. However, I think the intervals are more important because we're dealing with an oscillation. And so as long as the oscillation timings are accurate, then that's pretty much what we're looking for. And also, as you can see, the y position is predicted much more accurately than the x position. You can see the x sort of becomes further to the left of the experimental x becomes further to the left the further in time you get in relation to the model. So for example, at like about 0.75, 0.8 seconds, then it appears that the experimental model and the computational model are only maybe like 0.05 seconds off. Whereas if we're going around like 4.2 seconds on the x position graph, then you can see experimental and computational models are a little further apart there, maybe like 0.2, 0.25 seconds. So that's much more significant. However, the x position oscillation isn't what's primarily affected by the forces measured, by the energies measured. And so you would expect a little more variability in the x position graph than you would in the y position graph. So what does it mean? The energy principle satisfied. Yes, as although changes occur in the component values of energy, overall energy is conserved, delta E equals 0, because the energy principle. An isolated system experiences no work and thus has no change in energy. And you can see that in this graph, and I explained that earlier. Then for oscillation periods, there's another what does it mean question. So these are my calculations for x and y. I chose the 1.5 to 3 intervals, so you can kind of see those roughly here. Those oscillation periods could, the t values are different, right? And these oscillation periods could vary for a variety of reasons. First, they vary because the oscillation of the object in the recording is not perfectly circular, and there are pauses at the horizontal and vertical vertices that confound the model's findings. Alternatively, I could have made errors in tracking. But either way, because we are accounting primarily for y movement and potential energy of gravitation is included, which acts in the y direction, I would argue that the value for t from the y position graph is more reliable. And you can kind of see that here because the experimental and computational models are much more similar in the y than they are in the x. So thank you so much for watching, and I hope you guys learned a little bit about physics.